Here we can see an example of the routing table. And the routing table is basically a table which shows us the next steps in order to reach a specific destination. You can have static routes, direct links, and local links. Local links are the IP addresses configured on local interfaces, and direct links are usually showing us the path to other hosts in the same network as our local interface. So let's check a route in more detail. The first entry in the routing table is the destination network. Then we have the type of the route, or it will indicate which protocol it used to learn this route. And we can have static route, can have direct routes, and local routes, and routes learned via OSPF, BGP. We can have ISIS, and so on. The 5 here represents the administrative distance. The lower, the better. Each protocol has its own administrative distance, and it can be modified as you desire. Next, we have the route uptime, which is showing us for how many hours, days, or years a route is active. We can also have the next hop, which represents the next IP that it should reach in order to reach this network. This means that if a packet will come into the device, will enter the device, and it will have the destination IP address in its field. So let's say a packet will enter the device, and if the router will see that the destination address is in this network, it will send the packet to this IP address, which is the next hop address, via this interface, which is G001. Okay, so let's see that. Let's say that we have the incoming packet with source IP 13.13.1, and the destination IP is 11.11.11.1/24. The router will compare the destination IP with the entries in the routing table, and it will find out that this entry is the closest match. When I say closest match, I mean that the router will analyze all the bytes in the IP address, and the entry which resembles more with the destination IP will be chosen for routing. The traffic will be sent via the entry that was found to be the best. But what will happen when we'll have an incoming packet with the source IP of 13.13.13.1 and the destination IP, an address which is not present in the router's routing table? Since the router will not find any route that is matching this IP, it will drop the packet. Also, how to add a static route. So what is a static route? The static route is a manual entry in the routing table, which is teaching a router how to reach a certain network. So in this case, we are teaching the router to reach this network, and in order to reach this network, it should take this next hop, 10.10.10.1. We also can have dynamic routes, and in some cases we can have very big networks with a lot of routes, and configuring those routes will be time consuming, and we can also can have mistakes during the configuration. So we can use a dynamic routing protocol, which will dynamically learn the routes. We'll talk about the dynamic routes in the later lectures. So how does the routing happen? So the first step would be to find out the ARP. So when pinging PCC, we'll want to ping this PC, and the PCC does have a different IP address, which is not in the PCA's network. We have a configuration on PCA, which is called the default gateway, and usually you configure the default gateway, the IP address, on the router's interface where the host is connected. Let's say that if you have PCA connected into a switch, you will also configure the default gateway, the router's IP address. So PCA, as I said, will send an ARP request. It will populate its ARP table, but it will not send the ARP request to this host. It will send an ARP request to the default gateway. So the router will respond to the ARP request. Now PCA knows that in order to reach the default gateway, it should use the MAC address of A1, which is the router's MAC address from the interface where it is connected. PCA will generate a packet which will be sent to the default gateway. It will have a source address of itself and the destination IP of PCC. Also, we are talking about routing, but the layer 2 is also present here. What I want to say is that when data will leave a device, it will go through all 7 layers from top to bottom. And when data will enter on the device, it will go through all 7 layers from bottom to top. Which means that when our PC will send the traffic to other PC, it would have the data decapsulated, which means that the application layer will have a bigger packet. After it will move to the presentation layer, the size of the data will decrease. When it will reach session layer, the size of the data will decrease, and when it will reach the transport layer, the size of the data will be decreased, and so on. But when the data will receive here, it will enter as a physical layer. After that, the switch will add its data for the source and destination MAC, and the router will take this data, will not remove anything, and add some additional data in form of a packet. And if a TCP or UDP protocol is used, it will add also additional data here. So it's like a matryoshka, and physical layer is the smallest matryoshka, and as we move on to the application layer, we'll have the biggest matryoshka here, which will hold all other little matryoshkas from the first 6 layers. Okay, so the packet will be sent to the default gateway, and at this point the router will consult its routing table and will check for a route that is the best match by comparing the destination IP with the router's and routing table entries. Bit by the best match will win the election. So in this case, it found out that this is the best match, and the traffic should leave via port 3, which is this one. Okay, so the router routed the packet to PCC. So now PCC should also know the way back. So if the router doesn't have an ARP entry for PCC, it will send an ARP request that will populate its ARP table. It will check the routing table and will send the traffic to PCC via port 3. PCC will receive the traffic. It will check its ARP table, and if there is no ARP entry for the default gateway, it will send an ARP request to the router. After that, it will populate its ARP table and will compose a response to PCA, and this response will be sent to the router. And the router will check the routing table, and it will identify that in order to reach PCA, the traffic should exit via this interface. And also, if the router doesn't have an ARP entry, it will send an ARP request to PCA. And after that, it will route the response packet from PCA from PCC to PCA. So this is how the routing works. The PCs will continue to exchange data till they finish exchanging data. So if we'll go to our little lab right here, we can put a new capture here. Let's delete this old one and put a new capture here and here. So let's start the Wireshark for this one. And let's go ahead and ping PCC. See what is happening. So this is the traffic from PCA to the router. It will send an ARP request, as we discussed, asking who has the MAC address for this IP address. The router will respond, and it will start sending the ICMP packets. Also, what is happening on the PCC side? So in this case, the router will send the ARP request asking who has the MAC address for PCC's address, and the PCC will respond, and the communication will be established. Also, if we go to the router and issue show ARP, we will see that the ARP entries are saved on the router, and the router knows that in order to reach PCA, it should use this MAC address, and in order to reach PCC, it should use this MAC address. Thank you for watching. I hope that you are now more comfortable with the routers and you can understand the routing decisions that a router is doing.